So when this problem says that the voltage drop across the resistor is equal to the voltage drop across the capacitor, what they're telling you is that each one of them is half of the EMF, right? Because according to the loop rule, if you have an EMF and a switch and a resistor and a capacitor, right, then the loop rule tells you that the voltage drop across the resistor plus the voltage drop across the capacitor have to equal the EMF, right? So if the voltage drop across the resistor plus the voltage drop across the capacitor is equal to the EMF, and the EMF is 12, that means each of these must be 6. So, given that, I can say that the voltage drop across the resistor is equal to the current times the resistance. Well, our expression for current is it's the EMF over the resistance times e to the minus t over RC, right? Where this is the max current here. And then we're taking this thing and multiplying it by R, so the R's cancel out. And I'm left with 6 is equal to 12 times e to the minus t over RC, right? This is 6, the EMF is 12, so that means a half is equal to e to the minus t over RC. Now I take the natural log of both sides, and then I'm going to bring this up here. Then I'm left with the negative 0.693 is equal to 3.2 milliseconds divided by RC, and R is 600. Okay, so now if I solve for C is this is negative. So I can get rid of both of these negative signs. I get 3.2 times 10 to the minus 3 over 600 times 0.693. And that gives me a capacitance of 7.7 times 10 to the minus 6 farads, or 7.7 microfarads. That makes sense, because we're in the millisecond range, right? 10 to the minus 3. So in this millisecond range, we've already got the voltage drop across the resistor and the capacitor about equal to each other. So that means that the time constant, RC, or tau, needs to be in the range of 10 to the minus 3. Since the resistance is 10 to the second, roughly 10 to the third, then the capacitance needs to be in the 10 to the minus 6 range, so that when you multiply them together you get 10 to the minus 3. So that's a reasonable value for the capacitance.